how's it going? John Reagan with Ulshe AI and boardbrains.net. That's Ulshe, Ulshe.ai. And today, what I'm going to show you, this video is going to be a little long. So if you don't have a lot of time, maybe bookmark it and come back and watch it later. Because we are going to go over the app that I made for the AI Rust library that essentially allows you to do inference, build, train, agent, compute fabric networking. So it's actually what I should really call it is the Ulshe AI compute fabric, because what it does allows you through this app to take and make a fabric out of all of the machines that you have on your network. And I know a lot of you, if you work in AI, you're probably like, oh, you can't really do that, John. You need high speed NVLink, blah, blah, blah. I already figured that out. So to give you an idea, our tensor to tensor communication can run at about 500 kilobits. So really small and really fast, and will work over most general networks, home or otherwise. So let's move into this. So the reason I have this up right now is you can see OBS is taking up 1.5 GB. I've got a bunch of stuff in a text editor right now taking up 3.4 gigs, and the shell and everything else. Oh, did I not start my thing? Oh, you know what? Let me start the app. So I just started. You don't see it right now because it's on my other screen, but you can see that the dashboard. Oop, that's not gonna do anything for you. I'm gonna come over here. The dashboard right here is using 93 megs. It's using less. Running the Rust library setup and everything, UI and everything, is using less than 100 megs. So we're at 93 megs. And it's switching. I should have clicked on that one. Yeah. So we can see that it's using 93 megs, right? Anyway. Oh, where is it? There we go. So let me go ahead and bring that over so you can actually take a look at it. So this is the, and I'm going to look away from the camera because silly me, I have my camera over here, but the screen I'm using is over here. So I'm going to try and talk to you, but I'm going to be looking away a lot. So what we have here is the AI compute fabric built in Rust. It's essentially bare metal. There are some library dependencies I'm using right now, but eventually I'm going to get off those because the reason I made this in the first place is for my own AI models, my own architectures that I make that had proven to be really smart. And so I was thinking I needed this special OS that was going to be able to contain them better than what we currently have. And so I made a bare metal Rust kernel called Polymorph OS. And I needed a library to be able to run and train these AIs, so I started making a compatible Rust library for that. And as I made it, I realized, well, if it works this well for my stuff and I'm not using Python or PyTorch and it's super lean, then I could probably do this with other models, open weight models. And that's what I've been doing, is expanding this into a full application that has turned into a compute fabric for AI models. You can use this at home, you be able to use this in a lab, you'll be able to use this on a server system. And I'm going to show you some of the bits about why that is here. So currently we have the runtime, and this is where you can load up any of a bunch of different models that I've already converted to our MDO format. And yes, it is required to use the MDO format for this, and I'll get in and explain why that is. You can see we have some quanted down here to i8, which is comparable to most i4, if I remember, or normal i8 quant compression, and then our i4 is comparable to your average i4 quant compression. But I have an additional streaming compression that I'm working on that puts them on par with things like GGUF, GGUF, and some other ones. The real catch is with our converter, with our compression, it's lossless. We don't prune weights, we don't take anything out. It's all just mathematical compression, and you still get basically the same data resolution. You get the same amount of intelligence even with the smaller model. So what we have here, as you can see, is you can run those. So to walk you through it a little bit, let's start at the top. We have our runtime area, and this is where you would load a model for inference or multiple models if you have enough resources available. This is our converter. This is actually where you load the SafeTensors. You can see SafeTensors there. And right here is where you put your output for your model name. And then here's where you can actually select your precision. So I do everything in i32. I do everything in 32-bit precision, so my precisions in my models is never 16 or 8 or some of these. It's always at 32-bit precision. So every model I've made, every size I've made has always been at 32-bit precision. So I actually upscale some of your models because they run at a lower precision rate, and so I have to pad that a little bit in order to make some of my stuff work. It's okay, it doesn't add a lot, so it's really fine. And then we have our i8 performance, which takes it down basically, you can see 4 levels. And then i4, which is our deeper quant, and then the i4 ZSTD, which is our hyper quant. So ZSTD's been giving me some trouble. They have some security catches in there that make it a little hard to do the size file of streaming I need, and so I've got to work around that and figure it out. So anyway, this converter allows you to take these SafeTensor files and convert them to our MDO of various quantid sizes. So i32 is a little larger than what your normal file will be, not by much. i8 matches most 8-bit size quantizations or shrinking, however you want to put it. And then i4, same thing. And this one actually matches, when I've done it size-wise, the decompression is what kills me right now. It matches the kind of hyper quantized systems that are available from companies like Unsloth and Hugging Face. So the relative size is there, and the live streaming aspect is there. And again, in our quantization and our shrinking down of the model size so you can put on smaller stuff, our approach is generally lossless. So we don't prune, we don't trim, we get the same size models basically, and the same intelligence that exists in those larger models. So going over here to some of the other items, we have the benchmark, which isn't set up yet. This is under construction. This is going to be one of the areas where, as you start models, you can see what your token per second output is. You can see how many tokens you're using per request. You can see what basically your output in the benchmark areas would be, right? Over here we have the forge. Now the forge actually works pretty well. There's a couple things I have to tweak with it here, but it is set up so far to build our Ulshe AI models. You can see we have some settings here for you can do. But the other thing is I've been looking at setting up how to build just regular models. So you can actually, because I didn't actually, I reviewed your guys' stuff, your architectures like 2 years ago when I started working on this for other reasons, not to make AI. And I realized that they're cool, but they are nowhere near the type of models like what I'm building. So yeah, so you can essentially use this as well to build their models and just write off from raw. If you have your own curriculum, you have your own stuff you want to train them on. So we'll have all this set up so that based off the open weight and the architecture of the open weight models, you'll be able to just go ahead and directly build your own Mistral dense GQA or your own LLaMA Qwen 3 type or your own mixture of experts. And that's right, I have set it up for mixture of expert models as well. So that's going to be fun. I haven't played with that yet, but I've done some stuff. So here you can basically set to use our biological topologies or the standard transformer topologies. Here in the dojo, you can actually select your models for further reinforcement training. I'm still working on getting the i4 and i8s to where we can train them. And yes, you will be able to train our quantized models, which is not something you can normally do with a quantized model. So here you can pick what your lesson is, your lesson set, and then your learning rate and your max epochs per learning rate. And this provides add a factor jolts. That's a gradient refactoring that Google came out with a little bit ago. Works really well, and surprisingly, I'm able to get it to work so far on just about every model I've tried it on. So it even works on models that it wasn't initially used on. So it's kind of neat that way. Over here, we're going to have, oh, you know what? Let me get to the network brain first. We'll do cognitive swarm because the cognitive swarm is like your agent space. So, but when you say agent, you think of running one AI model and then plugging a bunch of these little front ends into it. So it's more like your one brain has 10 arms, right? When I say agent space, sure, we could do that. But when I say agent space, I mean you're running a cognitive model. You're running, as you can see, we have a frontal lobe, deep cortex, and the determinative verifier. So what we have here are three different models, which each run their own persona, you might say, or role within the passing of the prompt in the architecture. So, for example, this front lobe triage and IO, right? That's the front part that takes in your request. It'll then say, hey, oh, this request is way too complicated for me. I need to send it to the deep cortex or the discriminator for further analysis. And as I mentioned before, the protocol that I'm working on for this is with these tensors runs at about 500 kilobit full tensor to full tensor transfer. So that would normally be 16 megs about. So it actually ends up being relatively fast for the network transmission, and then you're just, waiting on the AI to process essentially. We have local REST API we're going to set up. We have the Synapse P2P bridge, which I'll explain in a minute, which goes into our networking protocol. And then we have API keys, as well as on the peer-to-peer, we run an encryption setup. So the API keys will run through the encrypted protocol. So everything you do is actually got a double type encryption, and I'll explain that too here in a minute. So we have the asymmetric graph routing, which is coming soon. We're working on this right now. So we have the user input to the frontal lobe. If it's more complex, like I said, it routes the higher one or the lower one. And these do kind of the final buffering review before it gets outputted to the user. This is actually going to help with hallucinations because we're getting multiple, not just one machine, not just one AI doing a whole bunch of stuff, but we're getting a lot of little AIs or even a big AI or a medium AI and a bunch of big AIs all doing these coordinated actions and efforts correcting each other. And there's additional, like what they call agent harnessing that can be done on the outside to really bring this all together a little better too. So I'm working on that stuff right now. The network brain is really what leads into the cognitive swarm. So because this app is so light and because the models are so small and the way we're setting it up, you can actually run this better on a unified memory platform such as a Mac Mini or a cell phone or tablet even, then you probably can running it on here. And even the times that I'm going to show you as far as generation goes, we have about a 100-fold total potential reduction in those times. So where right now the larger models are producing about a token every 3 to 5 seconds, we can actually see probably more like 3 to 5 tokens a second. And when you're talking like huge multi-billion parameter models, that's significant. That's a really significant gain. So here in Network Brain, what you see right now is it's just set up as the admin area. this is actually running a server, and then the client side I'm going to work on, which will be something you set up over here in the thing that's not popping up. I broke that one. I'll have to go back and fix it. I broke my gear. Anyway, it's a settings gear, and it has a little modal that pops up that gives you the ability to um, set up your file paths, your root file paths for the software, as well as set up your initial encryption keys and begin looking for other machines on the network, essentially, that are running this software. And so what this does, and this is why it's a compute fabric, is we're able to take whatever you're doing, whether it's your inference, whether it's the dojo training, or even full on training, and span that across GPUs, CPU, multiple machines within a given network. We treat the whole thing as one big fabric. So, and then we log in those machines and we utilize those resources to build or do the inference, basically question answer stuff with the AI. So it's kind of like a old school Beowulf cluster that lets you run your AI. um, this is kind of a neat feature to me because this is what gives us the ability for this type of a cognitive swarm. The idea being that you would run a smaller model on your cell phone, which from testing so far looks like it's going to run nice and cool, and it's not going to use a lot of resources, and it's not going to drain your battery, mostly because of optimizing the CPU processing and such. But beyond that, and we can leverage the GPU on there. There's a whole bunch of stuff I'm getting into on it right now. But then we go from your phone to your computer, or to a home server, or to a network server somewhere, cloud server, right? So you have this staged level of intelligence that your request gets routed through, thought about, and then brought back to you on the response. So it's not just one AI that's an agent, you're asking this agent, but you're actually really just talking to the same AI. You actually are leveraging different AIs and their capabilities to get things done, right? And it might take a little longer, but here and there, depending on the processing power you have. But what I'm finding so far is that where larger models will give you a fluffier, larger output, running it through the smaller model afterwards tightens that output down a lot to just the points. It's actually been pretty cool. So that's where the network brain comes in. So from here, you'll be able to look at the entirety of your compute fabric. You'll be able to select your nodes as a whole singular node, and then you'll be able to run your jobs that you're doing as far as like activating inference or doing training or whatever you have. So here you get your system logs. So anything that comes up pops in here, and then here will be the operating manual, which is going to be nice and long, explaining just how it all works, how to set it up, and how to do things. So now that we've gone over it, let me go ahead and give you a little demo. So just for fun, let's load up. Gemma was giving me problems because they have a different kind of a setup, but let me go ahead and we'll just load up. We'll do the 7BI8. We'll do it from tiered. Start it in the dream mode, and then I'll give it a little format. That's what the MICT protocol does, is it gives your prompts a formatting. This one's just a default format, but the idea will be that you can give them this structured format, and what I've found using it is it allows them to run through iterations well, and especially with like Qwen 72B, where it has the ability to play different roles, it will apply a human role to itself, ask itself questions as if it was the human, and then continue on with making things. So it's actually really neat, to me at least, in how it works. Some of you probably see this all the time, but I was actually really impressed with that. So let's, yeah, we'll do the 7B. We'll get that one started, and just to give you an idea, we'll pull this up while that starts. So you can see here, 7B is loading in GPU 1 because the way that our tiered inference works, it just scans for whatever cards you have, whatever RAM you have available, GPU, CPU. And I am working on the NPU. That's kind of the thing holding me up for really fast inference right now. And again, if this is running on a unified memory uh, platform like a Mac Mini or your cell phone, you're going to see about a 10 times increase in what I'm showing you now just because of how the GPU and CPU can hit the same RAM. So it makes it so they can talk to each other a lot quicker, they can do the math together a lot quicker, and that looks to be about a tenfold increase because it goes from about 28 to 32 gigabytes per second with the setup I'm running here. Whereas if you have a unified RAM setup, you'll get anywhere from 200 to 300. I mean, on the low end, you get about 100 gigabytes a second, but you're still talking a massive upgrade when you're trying to generate tokens from an AI. So just keep that in mind. So like when I show you it talking and stuff, that's why it's a little slower. So, oh, we already have it up. It's already talking. So you can see right here, it's running 11 gigs from tier Gemma. And so, you know, just for fun, let's say I want to have another one up and running. Let's just, you know what? Let's do a bigger one. Let's do the full size Gemma that I haven't quantized down yet. Again, we'll do it from tiered, all GPUs. We'll start it in dream mode just for fun. Blam, second window. So this will kick up. I've done like 5 windows before, 6 windows or something with various models too. So what we'll see and what I'll show you here in a second, if you remember, we only had the one up and it was, I think, about 11 gigs. So then we hit the max on this first card right here. You see the red bar, and the second card picked up the rest of it. And then when we go back over here and I show you, you're going to see, so this is both models running in on one card with part of the second model put onto the next card. And then we're using 53 gigabytes of RAM as a cache buffer. That's actually not system RAM in use by the app. That is a paging setup that I've done so that the OS will preload what it thinks you want ahead of time. So it gives it faster access. So, because it's also running off the hard drive. So it's pretty neat. So it's running across all these different components. We have the GPUs and the CPUs, and they're all working on this for these two. It's going to take a minute for this one to initialize because it is a lot bigger. Let's see here. And plus, with running the second one and taking up some of the compute power, it's going to take it a little bit of time. Something is neat, though, that I worked in here, and even though we're running these two, I could probably still run it. Let's find out. Is the tiered brain. So just to be kind to my system, we'll just run both of these in the low. And we'll do that on tiered waterfall too, just for fun to see how resilient it all is. And we'll get these other two models running on the tiered waterfall to see how it works. And it might crash. I haven't tried this much yet. So let's see. Oh, GPU's full, falling back to host. There we go. GPU's full, falling back to host. Very nice. So it's not crashing. It is initializing, but what we're going to see when I switch over is we're going to see a lot more RAM use here. And that's because it's loading it into the RAM that's available, and then it's streaming the rest from the SSD, right? I wouldn't recommend doing this from an HDD, a platter drive, because it is so slow. So yeah, so we see right here it's a 64 gigs, and if I pop back over here in a few minutes or a minute, this one will kick on too, because it's just two Gemma smaller models. They're usually a little quicker, but they're going to talk to each other. One of them's going to start in the draft mode, and it's going to talk, there we go, AI, and then the other one's going to confirm. So basically, what I've done with this is a dual model setup, dual brain. So one of them provides the answer, and the other one reviews it and confirms or tightens it all up. So It works pretty good, actually. I was pretty impressed. So right now we are running a total of, what, 14 plus 2 2Bs. So we're running 18 billion parameters right now. We've got both video cards saturated. We're engaging the CPU as well, right? Because we're on a proc, we need to do some other stuff. So we're engaging CPU, which does some things. And then we're streaming it from the hard drive as well. So this is pretty much, I would say, because of all the instances, this is about maxed out. I could probably start a few more. You know, let's try. It's not going to break anything. It's just going to crash the app. Why not? Let's see here. You know, we'll just do, we won't do another double brain. What the hell? Do another double brain. Yeah, falling back to host. And see, I have a good amount of RAM. I have 128 gigabytes of RAM on my system. So this thing will just keep going. I've got them running in auto, basically, with a little prompt, and they'll just sit here and dream. I did load up Qwen the other day, which is the other night, or sorry, last night. Jeez, my days. And gave it a prompt about making me a marketing plan. And when I got this morning, it was pretty good. I have to say, it covered a lot of stuff. It covered legalities and all kinds of things. So it actually does pretty good. And like I said, right now, my generation on these isn't really fast. And I mean, it's fast, but it's not really fast because I'm not fully leveraging the GPU, the CPU. Well, I'm leveraging the GPU and the CPU, but I'm still missing using the neural processing unit, which actually, it turns out, does really, really well with this type of math that I'm doing. So it would actually scream through this math, and so far I'm looking at roughly about a 10 times increase or decrease in the numbers with a higher increase in overall response, blah, blah, blah. Anyway, so just to show you here too, you can see in the terminal, I pulled over here that the tiered pager, we bootstrap those. I'm running in Rust. Yes, I have a bunch of warnings. Leave me alone. Warnings are just a warning. So it's all there. Yeah, it's been fun. All right, so that is pretty much it for the moment. Again, you got the runtime here, and you can run multiple models here. This just pages out. If I usually will stop them before I kill them, just as a practice, so I stop it, and it stops, and look at the little response. Generation halted by user. We could kill it if we want. Go away. And we'll see down here, terminate neural link, releasing VRAM. VRAM gets released. We'll just go one by one here. You can watch that. Oh yeah, down here we got some neat little things where you can set it to dream on another question of yours. And so it's interesting to do because they eventually get to a point where they do just start hallucinating or iterating the same things over and over and over again. And so what you can pull out of these is the good stuff and realize that they have limits. Right? There, we'll stop this guy or girl. I don't know. It. Stop it. And you can see that it's still sitting there in RAM, but if I click kill, now it's going to free up the VRAM again. We're just going down the line. So right now I have 2 of those 4 of the 2 billion parameter models, Gemma models running. Oops. And you can see we dropped most of our processing down after getting rid of the other ones. And you're going to see the VRAM drop significantly here because those are tiny little models. And even this is going to go down a lot. So this is all just crunching down now. It's going to quiet down now. So we have these 2 dual brains running. And what I haven't tried yet, and this will be fun for me. Let's see what we can do here. Where's that 72? Now let's run U. And for fun, let's run the i8 on the Gemma 7B. Sorry to be talking away from you. Somebody mentioned that my videos are really quiet, so I tried to turn up the gain and everything. It doesn't help that my screen's over here. I should put the camera over here, but the cord's really short. Okay, so we're all set up, and let's see if it works or crashes. That's how I operate. Let's see if I work or I broke it. Let's see if it works or if we broke it. Oh, we broke it. Get out the tools. So now the Qwen is going to take a minute because even though it's much smaller in size, I've actually got it down to about 45 gigabytes for this model, which isn't bad. It takes a little bit to hydrate, takes a little bit to get its questions up and stuff. And so this might be kind of the point where once it starts pumping it out, I just kind of end the video because you guys are going to sit here with me for a minute or two. So we've got, you see it, you can see that it's definitely got the RAM going. This RAM will come up to, and then it'll go ahead and load the rest of itself into RAM. But these ones are still going. They haven't stopped, right? They're still cranking along. You can see they're putting out. Then they're repeating or correcting each other, I should say. Let's see how this one works. It's been interesting. Oh, we filled it up, so now we're falling back to the host. That's a good sign. That means it's going. Oh, they both fell back to the host. Nice. So RAM's full. Now we're falling back to the processing. And what you'll see here, this is interesting to me to watch because I'm a nerd. But when it loads up, you start seeing the process of thought, like all these little blips, because I've separated out how it processes things to different processors. We can actually see when it's figuring something out. We can actually see when it's processing a certain layer. We can see when it's doing up here in the CPU. We can see when it's doing a rope calculation or a G-glue calculation. And then down here, we see when it's doing the forward components that exist in its calculation. So we can see it as it calculates through the layers and runs through it. So when you see these big blocks, it's doing all the layers, right? It's taking all your prompt and it's pushing it through, and we get to see that. And this, and because the way this is set up in a split, you'll see this first GPU process a bunch of stuff. And then when it's done, the second GPU will process a bunch of stuff. And then when you start seeing these little lines instead of a block, you know the CPU is about ready to kick on, and it'll start having little lines. Then we see the blips through the, basically the thought process as it spans through the different processors. So it's actually really neat to me, at least. You can see we're up to 103 gigs of RAM usage. We've got both cards maxed out. Like, I don't have much RAM left. So, but let's see if we got it running yet. Oh, it's gonna take a few minutes, but they are working. This one will boot in, and it will start producing a word setup just like these. So this dual brain, what you're seeing right now is essentially how the cognitive swarm is going to work, but across multiple AI models. So you'll be able to have very specialized AI models that you call to for certain things, to do certain things. And don't think this is just like a harness or app that I made. I made this so that I could make my own models, honestly, which are these ones, right? So I have about 17 different architectures that I've made over the past 2 years that I've tested that do work, that have a much higher cognitive density for for the base of parameters than the models that I've been playing with for the last like week and a half, 2 weeks, getting this set up for your legacy stuff, right? And I'm gonna tell you right now, the stuff you're doing is really cool. All right, if you work at an AI company and you're working with these normal transformers, the legacy transformer setup stuff, the stuff that everybody does, LLaMA or however you want to put it, it's cool. It really works. It's just that it is a very high-end SQL database system, and even though you guys say it has cognition and scariness and stuff, you still make it like an SQL database system. So I took that a whole lot farther in working with the MICT framework, the MICT structure that I derived out of something much larger And that which is actually the whole reason I'm even doing this. Like I'm not doing this because I wanted to make AI. I'm doing it because I wanted to test if this structure I figured out could possibly be a model of human quantum cognition. And if so, it would give all these additional efficiencies and stuff. And I'm actually seeing all those efficiencies. So I'm pretty well convinced there that it is a relative model of human quantum cognition. Um, and that's how my models are based. They are based on MIC. I've designed them pretty much biologically structured. They don't use the chimeras, don't use classic transformers. We have our own attention heads. We have our own all kinds of stuff that I put into these things. And even the newest one is like, whoa, like it's not even. It's off the hook. I can't even explain it to you right now. I don't want to get into it. We'll be here for another 20 minutes to an hour. So anyway, so the cognitive swarm leverages the dual brain runtime that we're seeing here. And we're still running, right? It crashed. No, we're still running. We're just on the second one now. So I've stalled almost long enough, as you can see. So what we'll see in that second one is probably a little longer than the top one because it's actually running two models for the most part out that. As much as it can. We'll see. It might be running the second model right off RAM. But so this and this will almost match, right, in size. But sometimes the second one's a lot larger because, as it turns out, on a home machine, a consumer PC, the second card is slot that you put it into is slower, a lot slower. Like 4 times slower. So it usually takes out a little longer. Oh, look, it might have gotten it done. Oh, yep, there we go. There's our little blip. There's our CPU blips. And so we should, any minute now, any second now actually, start seeing output from this third dual brain area. Oh, I don't have my mouse up there. No, should have done the show mouse. All right, well, next time. So this third one, the one all the way to the right that you see that says initializing, that one should start, because all of this means it's getting ready to pump out a bunch of words. It should start pumping out some words. We can see these two have already stopped. They're system ready, right? So they've both stopped. And if you look, they pretty much gave the exact same response to the exact same question. Now, how often do you get that? Yeah. So anyway, as this one's rolling, man. Oh, that's why. That's why. So with this dual brain, what I did is set up the 72B going to the 7B, right? So the 72B is going to take a minute, right? It takes it a minute to get going, but the 7B is obviously a little faster, so we should see it start popping out here real soon. Usually when you start seeing the cross blips, so there'll be these long lines on each side down here, which means the CPU, the crunching, basically the where it puts it all together to begin to construct its response. How you want to put that? So yeah, once this starts slowing down here in a second, and then we'll start seeing the little up and down lines coming through here, and that'll be it ready to talk, basically. So, and keep in mind, this whole time I'm running all these billions of parameters, I'm doing this video on the machine, right? I'm running other things like VS Code and a text editor with 3.5, 3.4 gigs standing right now. Actually, let me close that up. I don't need it open. Why it's open. Alright, so we'll get rid of that one. Oh, look, it sucked that memory right out. I was like, 33 gigs, yeah! So, Oh man, so this is what I've been up to. What have you guys been up to? All right. So let me just these ones are in here. They're already stopped, right? So this one should kick up any second now. Turn me into a liar, damn it. No, just for fun. Why not? Just for fun. Just because this little guy is taking a while. That's because I loaded the bigger model. Darn it. Or no, they're both i8. 72B is a little big. Come on already. So it's basically got to process that whole front we saw from this one, and then this whole back we saw from this one. Now, if I had the NPU turned on, which was giving me a lot of problems, oh, looks like the CPU is about to go, I think. Let's see here. Not go, but about to start talking. Um, if the NPU was working right now, all that chunking right here you see at the CPU would be gone. It would pretty much burn through the NPUs the way they're set up. It would burn through the math I've got in this, and it would smoke the GPU and the CPU at processing this stuff. It's freaking amazing. At least for inference. For training, it takes a little bit of different stuff. Oh, here we go. The human user. What are you doing? Additional insights. The centric approach emphasizes. They get so talky. They get weird. Let's see here. Are we ready to talk yet? Come on. So this one's stalling me hard. This is what you get when you start running a bunch of them though on one machine. So this is actually why I set up the network and distributed model. So I don't know about you, but as a techie, I have a bunch of computers here that just kind of sit around, don't do anything, right? Like I might go to this one or go to that one or go to this one or go to that one. But when I think about running something like this on machines I just have lying around, like a tablet that just sits there and does nothing, or a laptop that is older that maybe isn't as nice as the one you have now, but it's still fully functional, right? You can load these up, run a single or double model setup, and have that as part of your available cognitive network. So you would have that old laptop just sitting there running AI models. You hit it on the network, send your prompt, it spans out across your available AIs and gives you a consensus. It's basically like a group consensus out of that, or you route things accordingly, right? Depending on how that stuff is processing. So this is why I set that up big time, because if I run a huge model on this, like if I run something in the hundreds of billions of parameters or even multi-trillion parameters, it's going to slow down if I try to run other models on it. Oh, there we go. See, there's the little blips you get. As soon as you see these, you know it's about ready to respond. So it'll start kicking out words here in a sec. So what that does is it gives you distributed cognition, right? And instead of relying on one model, so those two are ready now. So instead of relying on one model to give you all your answers across multiple different things, you can actually rely on the models. Oh, it just systemed readied me. What a punk. Oh, you jerk. Oh, that's funny. Last time it freaking spit it out like crazy. 72B's output is a little much for these smaller models. So what I have to do, it looks like, is do a little breakdowning and then a reconstruction and assembly to the prompt on the other side. So yeah. Anyway, but kill you. Kill you. Now we're just running those. So anyway, you can see that stuff working. Here again, we have our quantization area where we convert the tensors over. We have our benchmark area where you'll be able to see how many tokens per second, things like that, that your AIs are producing, what they're benchmarking at for your setups. Here you'll be able to build from scratch our models, as well as what I call the legacy transformer, standard transformer models. So a lot of your open weight models that are out there right now, including mixture of experts. Here you'll be able to reinforce their training or train a current model on new things, and that does include the open weight models. Here you'll be able to, in Cognitive Swarm, you'll be able to leverage the totality of models that you own and host across your local network, whether that's phone to laptop, or phone to laptop to DevBox to server, or maybe even the Xbox someday, we'll see. But my dream is always this type of distributed computing system where what you have around you works together to process what you need, right? What you need processed. So it works just like that. Here in the network brain area is where you'll be able to connect to your other nodes through an encryption and encrypted keys. Additionally, when we send data tensor to tensor, you only see the numbers, right? So it really doesn't mean anything unless you actually have the tensor schematic set up and what it's doing at that time. The tensor transfer itself is kind of its own encryption, and then I'm adding encryption on top of that. So it'll be kind of double encrypted that way. Here in the system logs, you can see right now we're just keeping a single log, but this will get broken down into sub areas of things you're running. So as you start inference or a dual brain, these will get all logged and categorized for what you have. And then this area will be the manual. And then over here in this little gear that I'm not getting for some reason right now, I have to look at that. I think I might have blocked that one out earlier. I might have. Will be a little modal pop-up that'll give you where you can put in all your different stuff. So some of the upgrades I'm working on right now, especially here for the Forge, is in order to get training to work correctly on lower resource machines, you really need to break down these components and run them one at a time. So one of the big things I do is phase training. So because I don't freeze out my layers, I embrace that neuroplasticity, that ability to adjust and change that they have. I figured out that we can do stepped type training in a hierarchy that builds on top of the one before. So just like training a person, right? You give them foundational, then you give them the next one. And this is proven to develop what I've seen at least are hierarchical models where they will actually select a top 3 node process that allows them to work through problems effectively. It's really crazy shit. Also, what I've seen is in our architectures and the Ulshe AI architectures is a much smaller size for a much higher reasoning and reasoning rate, and much fewer pieces of data required to train. So the models that I make are highly optimized for content, relation, and intelligence. And if you review them and start looking at them, you'll understand why that is. Okay, so as a matter of fact, you might even be able to see a little bit. Let me click on here, we'll see. Yeah, so if you look in here, you'll see syntax, but you'll also see a TRM and a Debian, or Hebbian, and a cognitive threshold, and neuroplasticity learning rate, and adaptive learning rate. So there's a lot of really cool stuff I put into my models that you don't necessarily get in theirs. So when I click on theirs, notice it goes bye-bye. So the neater thing too is in doing this, like I said, my smaller models, my 44 million parameter model was giving me responses, at least from my testing, on par with their 1.1 billion LLaMA model, the tiny LLaMA. is actually doing better than that. So yeah, so that's it. That's the current status as Polymorph OS Triad. The AIs are so funny about naming. Everything's a Genesis, Triads, whatever. This is actually the Ulshe AI Compute Fabric application, and again, it is a Rust-based application, and it is designed. Are you still thinking? Oh yeah, it's not an answer. It's designed so that you can run and build and train and distributedly operate all those same functions with all kinds of AI models.